We were seeing about the functioning of light emitting diodes, which were emitting light in the visible region, which is the visible spectrum. And now we are going to see about infrared emitters. So these infrared emitters, they are going to emit light in the infrared region, which is not visible to our human eyes. Okay. So as we have seen about the different colors of light emitted from LED will depend on what material you are going to use, and the color is logically related by a term called wavelength, and that wavelength is related to the band gap energy of your device. Okay, so that's what we have seen in the last session. The color of the emitter light will depend on the material used, and different materials will have different band gap energy, and band gap will decide your lambda will decide your color. So that is how the relation is going to be. So remember, color means you the moment they say color of light means in when we are talking about light, we will not talk about the term called frequency. We talk about a more apt term called as wavelength. So whenever you say color, it correlates to the wavelength of light emitted only. Okay, so the infrared emission is possible when I am going to use only gallium arsenide as my material for my PN junction diode. So the infrared diodes are PN junction diodes made of gallium arsenide, and they emit IR light when they are forward biased. So this logic is same. When you are going to give forward bias to your PN junction diode, the depletion region will become smaller and smaller. So in that case, the electrons from N region will recombine with excess holes formed in the depletion region between the P and N-type material. See, the recombination happens in the depletion region only, and light is emitted from the depletion region. So the recombination will tend to restore the equilibrium carrier density, resulting in emission of photon. So we have seen about mass action law, right? So at any point, the law of conservation of energy has to be obeyed. So if electrons and holes are recombining, some form the energy has to be coming out, right? So that will result in the emission of photons. So the recombination of electrons and holes will result in the emission of photons. Here in gallium arsenide device, you cannot see the light emitted from the LED because it is going to emit infrared radiation. Infrared radiation is not visible to our human eyes. And you see here it peaks at around 0.9 mm, which ideally matches the response of photodiode and phototransistors. So the response is peaking at 0.9 mm. 0.9 mm is 900 nanometers. Okay, 900 nanometers means it will be close to the after red. See, 400 nanometers is violet, 700 nanometers is red. So after 900 means it comes after red. So it will have a peak response in the infrared region. Okay. So these infrared emitting diodes are used. They have a lot of applications: shaft encoder, data transmission systems, intrusion alarms, card and paper tape readers, and high density mounting applications. Only thing you know, when you give supply to LED, the LED will glow bright and emit light. But even when you give supply to this LED, it actually emits infrared light, but you cannot visually see anything. It will look like as if the circuit is not working, but actually the LED is emitting infrared radiation at the corresponding wavelength, which is not visible to our human eyes. So this LED can produce, see here, 150 microwatt of energy at 1.2 volt and 50 milliamperes of current. So why this infrared emitters is given a special topic is because we have several applications of infrared emitting diodes. Okay, so in shaft encoder, data transmission systems, intrusion alarms, card and paper tape readers, and other high density mounting applications.